Good afternoon, ladies and gentlemen. It's an honor and a pleasure for me to tell you about the Large Hadron Collider. I'll be talking mostly about an experiment, the CMS experiment. This has been 20 years since it was first conceived. It was installed and it is operating. And it took its first data last November, December of last year. And we've just published our first scientific paper last week. And this is going to be one of hundreds, perhaps thousands of scientific journals, papers that are going to come out in the next 15 to 20 years. Now this is a slide of the accelerator. So this is the machine, if you wish. Sometimes I'll refer to it as the machine. And the part that is visible are the interconnections between magnets. And these are technologically very advanced magnets. Imperial actually has played a very vital and integral role in the CMS experiment. Some of us were founders when we were a handful of people who conceived this experiment as one of them. And eventually it turned out to be that we have about 2,500 to 3,000 scientists and engineers from about 40 countries working on this experiment. Imperial is also involved in the second of the 4 experiments at the LHC, which is called the LHCb experiment, which looks at the origin of the difference between matter and antimatter. So I'll be giving you a small introduction on physics of it, the science, if you wish, and then go through the items of the accelerator, the detector, computing, and the prospects for discoveries. Now, particle physics is a modern name for a centuries-old effort to understand the fundamental laws of nature. So the experiment I'm describing is a particle physics experiment. Now, when I say it's a centuries-old effort, it is an effort, one can say it was started by Sir Isaac Newton when he noticed an apple falling, and from that he actually deduced that actually the moon is also falling on the Earth, and he combined gravity on the Earth with the gravity of the heavens. So that was one of the first unifications, if you like. And in all of these unifications, there are several of them, I might mention a few of them, great advances are made by society. There was the unification of electricity and magnetism from the work of Faraday, which was done by James Clerk Maxwell. And we all know what happened with the Industrial Revolution. And, for example, things like chemistry, we're in the chemistry department, chemistry and atomic physics, which led to the advent of quantum mechanics. And more recently, there was the unification of the weak interaction and the electromagnetic interaction. And one of the members of the Imperial College staff got a Nobel Prize for that some 20-odd years ago, Abdus Salam. And so these things actually lead and propagate into society, and it changes the way we perceive things and the way we live. Now, the aim here is to answer 2 fundamental questions. One is, what are the elementary constituents of matter, and what are the forces that control their behavior at the most basic level? I'm an experimentalist, so experimentally what it means is that if you want to look at something deep inside, you actually make it collide. It breaks up, and then you start looking what's inside. So the idea here is to get particles to collide. In the case here, it would be protons to collide at very high energies. And you look at the resulting products as they come out. And you measure the energy, the direction, and the identity of all the particles that come out, and deduce what has happened. So the mission statement is rather simple, but it leads to some very complex and challenging instruments. Now, we're all very familiar with the structure of matter, perhaps, so we can take any piece of material and you break it up. Sometimes it's as molecules and atoms, perhaps sometimes in crystals and regular lattices. And when you look inside the atom, you find an electron and a nucleus. If you go inside the nucleus, you find a neutron and a proton. And you go look inside the neutron and proton, you find what are called quarks. So this essentially summarizes the physics of the last century, if you wish. So I'll show you 16 letters which actually comprise our understanding of what the fundamental constituents of matter and the mediators of the forces between them are. And it's this one. It's called the Standard Model of Particle Physics. It contains the quantum theories of 3 of the 4 fundamental interactions. The only one that is missing is gravity, and we don't have much of a clue how to bring that in. We may get some clues from the results of the LHC experiments. Now, normal matter only requires the leftmost column. There are 4 columns. 3 columns are of quarks and 1 column of the carriers of the forces. We only need the leftmost column to describe any matter that you see in front of you or in the stars and so on. But nature seems to have produced 2 further copies. And it turns out that these 2 further copies are at least needed if we are to explain why we are matter-dominated. Because in the early part of the universe, right at the moment of the Big Bang, matter and antimatter were created in equal quantities. Somehow, matter has won out, 1 part in a billion, in fact. Now, there are some problems with this standard model. There are some fundamental problems which need to be solved, and they probably will find solutions at the LHC energy, and that's what makes the LHC energy something special. These particles have different masses. Just look at the numbers. The mass of a proton is about 1,000 in those units. So you have a very large range of possible masses, and we don't understand how mass arises. And mass is the source of gravity, the charge of gravity. It has the same meaning, in a sense, as electric charge, and we don't really quite understand. We know what Newton told us. We also know what Einstein told us about mass, in the sense that there are some equations. If you want to push something to a given acceleration, if it's got a high mass, then you have to give it a bigger kick. That's Newton. And Einstein told us E equals mc squared. Mass and energy are convertible currencies, but we don't quite understand how it arises. There are other things that happen. Mathematically, this model, which is very successful, it's the most successful scientific theory, arguably, that we have as an outcome of the 20th century of science, if you wish. It mathematically breaks down at the energies of the LHC. And it has some consequences, like there's new symmetries could be present. Maybe we live in more dimensions than the 4 that we know. So these are the sort of physics that we're trying to, or the science we're trying to discover. This study now requires accelerators, because we have to go to very high energies and smash the particles together. The higher energy, the better it is, and I'll explain why. And so these are the powerful machines that accelerate these particles to very high energies. Then we need detectors to detect the particles that come out of the collisions. So these are gigantic instruments. You can see the CMS detector some years ago. Inside that ring there are some people standing, and you can then get the scale of this instrument. Then we also need very, very powerful farms of computers, very high computing capacity, because we have to collect, store, and analyze this data, and these are distributed all over the world. And then finally, people. So it's only a worldwide community of thousands of scientists and engineers that can actually build such things, because we need their resources and their talents to do this. So let me start with the accelerator. So the idea, as I said, is to accelerate particles to high energies, and I'm going to use 3 equations, and I hope you bear with me. The higher energies allow us to look deeper into matter, because if you want to look deep into matter, you have to use a microscope, which has a radiation of a wavelength which is small, or energy which is very large, because the energy is proportional to 1 over the size. Smaller the size, higher the energy. And this is from a physicist, de Broglie, beginning of last century. So these are powerful microscopes, the most powerful microscopes ever built. We want to discover new and heavy particles which have not been discovered so far. So there we use the Einstein's relation, that energy and mass are convertible currencies. So if you want to look at something which is very heavy, you have to have very high energy to convert that energy into mass. And that's what then we observe, and that's Einstein. And another condition is that the energy is proportional to temperature. So higher the temperature, higher the energies, and this comes from another physicist, Boltzmann, an Austrian guy. And this then connects us back to the early universe, because the early universe was supposed to be extremely hot. So when we have very high energies, we're actually going back to the early times when the universe was very hot. So this makes these instruments like telescopes. We're looking back in time. And this is what telescopes do. So these instruments then allow us to revisit the earlier moments of our ancestral universe and to observe phenomena and particles normally that no longer visible in our or existing in our time. And all of this is done in a controlled way in the laboratory. Now, the LHC timeline is a very long one. The first notions of having this accelerated experiments was in the early 80s. And the move to approval was in 1996. Between 1990 and 1996, a lot of work was done in conceiving and then doing the R&D and then prototyping to launch the construction of the accelerator and the experiments. The construction began in 1998, and in 2008, we finished, installed, and started running, and the LHC had this first operation and this infamous incident where a lot of damage was done by one of the connections between the magnets that I showed you in my first transparency was not perfect and created a small amount of heat, which actually led to a positive feedback reaction. Now, the data have been, we've started taking data. The first paper has been published from the CMS experiment. We foresee about 20 years of data taking. So let me come to the where it is. So this is the CERN site. So this is the Lake of Geneva at the top here. And that's the airport of Geneva. And this is a ring, which is 27 kilometers long. It's about 100 meters underground. There are the mountains on this side and the lake there and the mountains on that side. And this is a CERN site here. It has about 5 or 6 ring accelerators. You can see a smaller one here and quite a few smaller ones in here, which I'll show you in a second. So the CMS and the LHCb experiments are the ones that the Imperial College groups are involved in. They're highlighted there. So the protons start the journey in a bottle of gas. It's a hydrogen gas. So in this, this is an animation. What you'll see is the protons are stripped, the electrons are stripped out of the atoms of the hydrogen, and then you're left with the nucleus, which is a proton, and then these protons are accelerated by a linear accelerator, then taken up to about tens of percent of the mass of the proton, fed into a ring accelerator, which takes it to about 1.5 times the mass of the proton, and then into a bigger one, 20 times, and the one that I pointed out to about 450 times, and finally into the LHC, where it goes to about 7,000 times. And so this is the animation. You will, oh, sorry, I should actually click on that. So you can also see the geography where as the particles are fed one way in one case and the other way, and they're made to then collide at various points where the experiments are found in the cavern. So this is the CMS experiment, which is diametrically opposite from the main site of CERN. So now the accelerator actually accelerates protons, and you use electric fields to do that, and they're guided around by very powerful magnets, and you can see them on the left-hand side. Now, these are magnets which are very, very powerful, about 10,000 amps which run them. They're superconducting. They use superfluid helium. And we use hundreds and hundreds of tons of superfluid helium, and this was a substance discovered by Kamerlingh Ernest about 100 years ago. It was a research material, and now it's an engineering material. It has very nice engineering properties. Now, the protons travel in a tube, which is about this size, about 5 centimeters in diameter, and inside there, the vacuum is better than the vacuum in outer space, because you do not want the protons to collide in gas particles. And because of the superconductivity, superfluid helium, the temperature is colder than outer space. And these are just numbers with respect to the current accelerators. Now, let me say a few words about the sociology and the construction of these experiments. These are perhaps the most complex scientific instruments ever built. And let me just say something about the sociology and bring out Imperial College through this transparency. I mentioned there are about 3,000 scientists and engineers from about 38 countries. And our group from Imperial is one of the 180. It's one of the 5 biggest groups, in fact. And we were the originators of the experiment. So we conceived it, and we also developed many of the technologies that are used in this experiment, and silicon tracking and radiation-hard electronics. Some of the work was done here in the physics department. And in some of the instruments, I'll tell you more about it when I get there. And now we're moving into the science exploitation phase of the experiment. And so we'll all be actually quite interested working in the results and the data analysis. Now, leading these experiments, so these are global, worldwide experiments. And so they have universities, some of which were mentioned earlier, places like Harvard, Yale, Princeton, Caltech, and other universities from the world. And so in the CMS experiment, so there are 4 LHC experiments. CMS and LHCb are the ones that Imperial is involved in. I was the deputy spokesperson. Spokesperson is a project leader, if you wish. And that person is responsible for everything that happens inside the experiment, whether it's scientific, financial, technical, managerial, or industrial, whatever. So it's a project leader, and in our field we call that person the spokesperson. So I was the spokesperson of the experiment until end of last year. And another experiment is led by another member of the Imperial College Physics Department, the LHC experiment. So we are playing quite fundamental roles in these experiments, which are acknowledged worldwide. I think one of the things I should say, we can do these kind of things because we do get a lot of support from our institution. There's constant support and backup, and the periods are long. The 20 years have already elapsed, and this comes from the group leaders, the physics departments, the deans, and the rectors. In fact, the last 2 rectors have already been to the experiment. I know Sir Keith actually visited CMS and CERN some years ago. Now, the experiment challenge is that we have 1 billion pairs of protons interacting every second, and that leads to a few consequences which are pretty challenging in terms of instrumentation. They lead, each collision leads to some like 100 particles. So when you have 1 billion, you have 100 billion particles which are flooding out from the point of interaction. And then these lead to very high radiation levels for instruments which are about 4 centimeters away, going up to about 15 meters. And so you need to actually develop instruments which survive this radiation level, and electronics which survive this radiation level. These existed 20 years ago only in military space industries. And they also lead to enormous amounts of data, about 40 terabytes per second. There is no way we can digest this kind of stuff, and I'll come back to that point. And there is high radiation levels and require a lot of R&D and prototyping and industrial production. Now let me just give you some idea of what an experiment is. So an experiment is sort of a cylindrical onion surrounding the point of interaction. The beams come and interact, and you surround that with a cylindrical onion. A Hanji physics experiment has about 4 principal layers, and the idea of each of these layers is to measure a certain quantity, and all together they allow us to do what I mentioned earlier, to measure the direction, identity, energy of all the particles that are produced. And they leave distinctive patterns, so you can actually work out what particle went where, as you can see on this transparency here. Now this is now a cut of that cylindrical onion, if you like, at the midplane. And this is the CMS experiment. And you can see the various layers. In this layer is the first one, silicon detectors. Imperial College played a significant role here. And the next one is lead tungsten crystals. I'll say a few words about that. This measures the energies of electrons and photons. And then this is a magnet. It's the most powerful solenoid ever built. It has a field which is about 100,000 times the field of the Earth. And it has about 20,000 amps going through the coil which actually generates this magnetic field. And this is the muon system, detects particles. The only particles that reach this area here are muons or neutrinos. Neutrinos never interact, and they leave no trace, and we have to deduce their presence by looking at an imbalance, something going this way and nothing balancing it. Now, so those are the 4 layers that I mentioned, and this is now just a blow-up of this instrument, if you like, to give you a feeling for how the experiment is built up. Now this is deconstructed, and you can see the protons will be coming in, interacting, and you get the events. Now I'll show you the real events. This is a simulation later on in the talk, where we have actually measured the points as such and reconstructed things of this nature. So this is the LHCb detector. It's a slightly different geometry, and I won't actually go too much into that. And that experiment is actually meant to understand the difference in matter and antimatter. Nature has this preference for matter over antimatter. Why is that the case? And here again, there were instruments which were built at Imperial, for example. This instrument was built, and parts of it was built here. Now, in these experiments, it's not only the science in a sense. To get to the science, we have had to do a lot of engineering. And I'll give you some feel for that. So this is a superconducting magnet. These plots, this is the stored energy. It's an enormous amount of energy that is stored inside this magnet. It's about 3 gigajoules. It's energy that can melt 18 tons of gold if it was released uncontrollably, in a sense. What I wanted to pass across is that we are way above anything that was previously attempted. And there are many, many plots of this nature of the instruments that we've built where you can show this is 1 order of magnitude or 2 orders of magnitude bigger, more complex than what was attempted before. Now, this is the magnet in it when it's finished. It has a conductor, which is it's a plate, in fact, it's not even a wire, which is wound around. And it has about 5 countries, industries from 5 European countries, which actually were involved in the construction of this thing. It took about 10 years to get from the right-hand side to the left-hand side. And this is the conductor. That's the coil, if you wish, which is sitting inside a vacuum vessel. What you see on the left-hand side is the vacuum vessel, and over here is the liquid helium that comes in to cool this thing to the superconducting temperature, so you can put 20,000 amps through this wire here, which is only about 32 wires of 1 millimeter diameter. They're made of niobium and titanium. Now, another thing we had to do, all of these things usually are driven by the physics, so we want to do the physics, and we have to build the instrument that can do the physics that we wish to do. In this case, the design goal for this second layer, which is made of lead tungstate crystals, was to detect the Higgs boson. It has a distinctive decay, and it's conjectured to be at a place where this is the only distinctive decay we can, final product, if you like. The Higgs is produced and goes into 2 high-energy photons, and we have to pick up the energy and the direction of these photons and measure it very precisely. If you measure it very precisely, then it is easier to observe. So we were pushed into developing this particular instrument. And now, to give you some idea of the timeline, we started with a sample of some Russians brought a few centimeter cubes of this substance to us in the early 90s. And they thought, well, this could be something you can use for this instrument. It looked promising, but it was very yellow, and the substance has to be radiation hard, so it should be very clear. And so we had to work on improving the radiation hardness. We had to work on purity of the raw materials, lead oxide, tungsten oxide, the balance of the 2 materials, and remove any defects, because it's a crystal, it's a lattice structure, and you have to dope it with some special materials. And then you have to prototype, go into test beams to see if the performance is what will allow you to do the physics you want to do, and then you have to manufacture. In fact, for the manufacture, we had to convert a factory, a whole factory in the Russian industrial military sector, and bring in new quality control methods into that factory, and that factory worked for us for 10 years. We started with the samples about a few cc's. We needed 10 cubic meters of it, and there are 75,000 of these crystals, and each crystal takes about 3 days to grow. And this is one of the ovens. There are about 150 ovens which were running round the clock for 10 years to produce the crystals for us. So these are the crystals which are the light. In fact, what happens is the photon comes in, creates showers of charged particles which emit light. The light is then picked up by photo devices. These photo devices also did not really exist. They only existed in research samples when we started about 20 years ago. There are 135,000 of these objects inside the detector. And these are objects that are finding applications now in positron emission tomography cameras. So we have to turn these crystals, they're about this big, and support them around the interaction region, no dead spaces. They have to be supported independent, and there again engineering is very important. So they're supported by carbon fiber structures which are about 300 microns thick, and there has to be very little space in between the crystals. And they're put into various collections, and the next thing we have to do is to put a huge amount of electronics to read out these things, because these things are operating with the clock speeds of 40 megahertz. That's the number of times the bunches of protons cross each other in the design performance. And after about 10 years, you install these instruments, and that's what it looked like about 1.5 years ago when it was installed. Now, these are instruments which have come from all over the world. So instruments where the governments give money to the scientists of that country to produce materials and detectors which are then sent to Geneva and installed. So let me quickly give you a quick guide for the last 10 years, if you like. So this is a surface site about 10 years ago. The experiment was assembled on the surface building, that's the size of a car here, and there's a huge pit here. And the experiment was assembled here and then lowered down this shaft, and the cavern is 100 meters underground. And just to give you another flavor of engineering, this time civil engineering, I mentioned there were some mountains on the left-hand side of this transparency, and there's a lake on the right-hand side. And about 40 meters underground, there's a huge, very powerful sheet of water which goes down into the lake. We knew about it, but we didn't quite understand the force. So normally when you go through this kind of material, you put brine at minus 20 degrees and freeze it, and then you drill through it. And the brine was just being completely destroyed, and we had to use liquid nitrogen to freeze to create permafrost, drill through it, line it with concrete, and then remove the liquid nitrogen pipes. So this was the outer casing of the experiment, the magnet assembled in 2003. Another thing we had to do was also try to find resources from wherever we could, and one of the Russian contributions was the shell casings of the decommissioned shells of the Russian Northern Fleet. So this picture is taken in Murmansk, and there are about 1 million shell casings which were melted down, and this was done in St. Petersburg, turned into raw plates which were sent to Minsk for machining, and then taken to CERN where they were actually assembled, and that is now a detector. This was the situation in 2006. This high activity on the surface building, and the thing that I was talking to you about just a few minutes ago is the, I've lost the cursor, is sitting here actually, all the way through there. Then we had to take the detector down, because that's where the accelerator is, that's where the collisions will take place. It's 100 meters underground, so we got delivery of the cavern in 2004. And then we started actually lowering the pieces of the detectors. This is one of the pieces, the biggest piece, about 2,500 tons. You'll see that it's resting on this cover plate here. There's a crane which is on the outside of this building, and it's going to lower this object 100 meters underground. This plate here is going to move outwards because it's being supported by the crane which is on the outside of this building, and then gently lower. It will take about it took 10 hours, but this one doesn't take 10 hours. So, not that fast. So this is now a time-lapse picture, so you can see the cover plate going down, and this object which is 2,500 tons in weight, and that's the coil as such, the magnet going down. And as I said, it takes about 10 hours. Here you can see the crane on the outside now. And down below it's going to be received and then moved inside. This is the cavern, underground cavern, which is about 100 meters, as I mentioned earlier. And eventually you'll see the strands will loosen. That tells you that the object itself has landed, as you noticed here, it has loosened. So that's another engineering feat. It's never been attempted before, and this has been so successful, and the future experiments will probably use a similar method. Now, this is quite bold, as you see. There's nothing there. There are a lot of detectors which have to go in there. So in the assembly process, we have to bring these detectors. I showed you the electromagnetic crystal calorimeter. That has to go in there. And so we have actually to take a lot of cables out. And this is the situation of that object about 7 months later. It's completely lined with services, water, cooling things, other cooling fluids, optical fibers, low voltage, high voltage distributions, and so on. This took about 50,000 man hours. And this is the central system going in. And that's the situation about 1.5 years ago when the detector was ready to close. Now here you can see the beam pipe here, for example. So everything has been connected and it's ready to take the beams, and the experiment was essentially closed immediately afterwards, and this is the situation at the moment, for example, in the cabin downstairs. Beam is supposed to be coming back in a week on Monday. So now let me go to some other features of the experiment. So I mentioned there are 40 million times the bunches of protons cross each other, and the interesting event could be in any one of them. So we have to select them. We can only record about 300 of them. So we look at what happens at 90 degrees from the beam line, and this is a simulation of a Higgs event, for example. So if there's a lot of energy going at 90 degrees, that's the interesting thing, and we pull it out and record it for further analysis offline. So in a sense, the experiment I've just shown you can be considered to be a digital camera. It is a digital camera which has 100 megapixels, because that's the number of discrete electronics channels it has. And it is taking pictures at 40 million, so it's a 15,000 ton object. It's not an ordinary camera. It takes 40 million pictures, because that's the number of times the bunches cross, but it's taking pictures of the time about 1/100th of a nanosecond after the Big Bang, of events that were occurring at that time. And from there we will deduce what was present in the universe at that time. And of course, each of the pictures has a size of about a digital camera picture, about a megabyte. And that then tells you that you have a massive computing problem. And so for that, the worldwide grid was set up to analyze the data from these experiments. Just to give you the computing grid, sorry. The World Wide Web, as you probably know, was invented at CERN and provides seamless access to information that is stored in millions of different geographical locations. The grid here is doing something slightly different. It's an infrastructure that provides seamless access to computing power and data storage capacity, which is distributed around the world. And this is also something which we developed. This is a monitoring system of what's happening in the worldwide grid, which is done by the Imperial College people. So this gives you some idea of the amount of work that has been done and the technologies that have been pushed. And it goes across all sorts of disciplines: engineering, instrumentation, electronics, computing, networking, organizational and distributed analysis. So now we come to the point where the detectors were ready to start taking data. So first we used cosmic rays. So the cosmic rays, very high energy cosmic rays, are impinging on the upper atmosphere. They lead to showers, and they lead to particles called muons, which can penetrate 100 meters of Earth and go through the experiment. And we record their passage. These are real events that I was showing you, which were passing by. And from there we deduced actually the experiment was working according to the design specifications. So we knew already about a year and a half ago the experiment will work quite well. So in fact, we recorded a lot of data, and we already published about 20-odd papers which explain the performance of the experiment. Come 10th of September 2008, the beams were injected into the LHC, and it was a very successful launch, but a few days later there was this incident where a lot of damage was done to about half a kilometer inside the tunnel, which was essentially a shock wave which traveled down the tunnel on one side, dislodged many of the magnets and broke the interconnections, and it's taken us about a year to repair those things. So after 1 year of repairs and consolidation, the beams were injected again on 20th of November last year, and the progress was very fast. The machine actually works very well. After 3 days we had the first proton collisions. After about 9 days we were accelerated to about 1.2 TeV, which is higher than what has previously been achieved. After 16 days we had collisions, and about 18 days we had collisions at the high energy. And the program for this year is we go back on again and ramp up the energy to 3.5 TeV per beam, and then increase the collision rates from about hundreds to about order of 10 million per second by the end of this year. So that's one way, because we're looking for very rare processes, and we need to have very large numbers of protons interacting per second and dig them out, if you wish. And already by the end of this year, we should be moving into unexplored territory. Although we have a long period ahead of us, we'll be starting to explore unexplored territory towards the end of this year, and of course then this will be the leading accelerator in the world. This just gives you some feeling for, these are traces of two beams which have been injected, and if the beam intensity goes down, the beams are removed from the machine, and a new set of protons is injected, and you can see four sets of protons which have been injected inside the machine. And this is one of the events. So the points here are the points of the first layer. There are about 10 layers of silicon detectors, which then localize the charge track, in this case, to about 15 micron accuracy in a detector which has an overall dimension of about 15 meters. And so the tracks there are the reconstructed tracks from the computing, from the software, if you wish. And the reds are the second layer firing, the blues are the third layer firing. There's not much that is going into the fourth layer, so that's not displayed here. And from these kind of things, we can start looking at the physics quantities. And so these are, you see circles in some of this. This is the same event as the previous one. You see conglomerations of energy. And these are quarks and gluons, which are actually dressing themselves into collimated bunches of particles. and these are coming from the primary interactions from inside the proton. And these are the sort of quantities which we'll be looking at in making our discoveries, hopefully, which we will be doing soon. These are just some plots of some quantities, which actually the reason for showing this is that these are known particles. We know what the central values are, if you wish, and they're being reproduced to 1 part in 10 to the 4. Some of these plots were produced the day after the data were taken. And with these complex instruments, with the whole chain working, it was not an obvious given that this would be the case. And it was the case. So this is CMS on the left-hand side, LHCb on the right-hand side, which checks the first layer. This one, the plots below, check the second layer, that it's working as we expect. And we published the first paper, which was a simple one, no ground-breaking stuff yet. This is just the particle multiplicities of interactions, how many particles are produced when protons interact at high energies. And then when we continue to 2010, the first thing now we have to do, we know the experiment works very well, the detectors work very well. The first thing we've got to do next is, does it produce known physics at the rates we expect? Because if we are looking for something rare or unexpected, we must know that what is expected is being measured correctly. And so these are the particles which merited Nobel Prizes about 20 years ago, and they're used as backgrounds and standard candles, if you wish. So these are the W particles. Now what we're looking for new physics is an event of this type, where you notice that the beam pipe is shown, there's a lot of energy going on one side, there's nothing on the other side. And some of the new physics actually predicts that to happen, but the events on the left can also have some signatures of this nature. So we need to look at the rates of these things, and clearly that is going to be the challenge. So in conclusion, the LHC project, both the accelerator and the experiments, was conceived and designed to tackle fundamental questions in particle physics and, dare I say, in science. The accelerator and the experiments are unprecedented in complexity and will operate in an unprecedented and hostile environment. And driven by the science we want to do, many technologies have been pushed to their limits. The project has required a long and painstaking effort on a global scale. The accelerator and the experiments are unparalleled scientific instruments. They are both, at the same time, the most powerful microscopes as well as the most powerful telescopes. So 2009 conclusion and the outlook. So after about 20 years of design, construction, the second half of the journey of the extraction of physics has started in earnest. The accelerator and the experiments have had a good start and performed very well. The LHC has delivered first proton-proton collisions at 900 times the mass of the proton and 2,360 times the mass of the proton, the highest energies achieved so far. The CMS experiment itself, 99% of the sub-detected electronic channels are operational with high data-taking efficiencies. The data can be analyzed very rapidly. This tells us that all the chains are working well, the detector chains, the software chains, the computing chains, and the human chains. And the performance we're finding is very good, in agreement with design expectation. However, this is just the beginning, but it's a tremendous encouragement for the future, and there's a long and interesting journey ahead. Finally, all the expectations are that what we will find at the LHC will reform our understanding of nature at the most fundamental level, and one has to be reminded of the fact that only experiments reveal or confirm nature's inner secrets. Thank you.